one, there's a lot of videos in it. You don't have to necessarily watch them all, but I would encourage you to watch this one. So I've kind of done a lot of examples to make sure I've kind of hit everything that students typically have questions on in this section, and I'll talk about it even in the next sections. So this last thing, which there's problems like this on your homework. I mean, when you're given a graph of the derivative, you can find a whole bunch of information about the original function. You can find where it's decreasing, where it has extrema, max, mins, where it has critical points. And then what you can do is you can get a possible, and it is a possible sketch. And my sketches that I do on here might actually be a little different than the ones I've done in the completed notes, just on purpose, to give you an example of you basically need to have the right shape, but different students, all of you technically could, or there's infinitely many different possible original functions, but they should have the same basic shapes. Where they're located on the graph is where the possibilities come into play. Alright, so the first example here is a simple case where I've got a derivative that's a line. Alright, so the blue function here is my derivative. So the derivative tells me a lot of information though, right? My derivative, so first of all, get all the information from the derivative. So they mark off this point here. That point's important. That 4 is where it crosses the x-axis. That's its 0. So if you remember, the derivative is 0, right, or has an x-intercept. It's 0 on my function, is where we have a critical value. On the original, which I don't have the original, but it would reflect as a critical value on my original. And not only is it a critical value, but it'd be a critical value where I have a horizontal tangent to my original function. And so the 0 in this case at 4. So at x equals 4, so I'd have a critical point at 4, f of 4. Now I don't know what f of 4 is. That's where your answers could vary. Your f of 4 could be in a different spot than somebody else's f of 4, because I don't know what the original function is. But I know at 4, at the x value 4, I should have a critical point. Not only should I have a critical point, but I know what type of critical point it is. It's a critical point where I've got a horizontal tangent. Alright, so that's the critical point. Then, I know when my derivative is positive, greater than 0. When its graph is above the x-axis. Well, the graph is above the x-axis on this piece, right? This piece from 4 to infinity, right? 4 going off of forever. My derivative is positive. So over the interval 4 to infinity, the derivative is positive. The slopes are positive, which means the original function f of x, the original, is increasing, right? If I've got positive slopes, my function's increasing from 4 to infinity. Now, how fast, how slow, I don't know, but I know it should be moving up, right? Increasing meaning it should be moving in the upward direction. All right, so I know I have a critical point. I know it should be increasing from 4 to infinity. I also know when my derivative is negative, right? It's negative when its graph is below the x-axis. Well, the graph is below the x-axis on this piece, right? That's negative there. And so from negative infinity to 4, right, that whole piece between negative infinity and 4, my derivative is negative. So from negative infinity to 4, the derivative is negative, which means my slopes are negative. And so that tells me the original function f of x, the original, is decreasing. I don't know how fast or slow, but I know it should be moving down between negative infinity and 4. Alright, it should be decreasing. Now, how fast or how slow it's decreasing, I don't know, but I know it should be moving down to the critical point between negative infinity to positive 4. Alright, so based on that information, again, it should be moving down, should have a stopping point at 4, I can sketch a possible graph of the original function. Now, on the notes that I have filled out, I actually drew it on this graph, but I'm actually going to draw a second graph below this. So I'm going to draw a new grid. And again, I'm going to mark off 4 for sort of the important moment, my x equals 4. And so this is where your answers can vary, but it should have the same basic shape. At 4, I have a critical, so where you draw your critical value, it's up to you. You can draw it above, below, wherever. So I'm going to draw it below to make it different than what I have in my completed notes. So again, what that function value is, it'd be some negative value down here. That would be my f of 4. My y value, again, is some unknown. I'm just guessing. I'm just throwing it on here. Alright, but I know that should be a stopping point. That's a critical moment. Then I know from negative infinity to 4, right, negative infinity to 4, it should be moving down, so it's moving downward towards that critical moment. How fast it moves down towards that critical moment, well, that's where you could draw it a little differently. But I know my function should be moving down towards that critical moment. It should be decreasing. Then it stops. From 4 to infinity, it switches directions, right? From 4 to infinity, it should now be moving in the upward direction, and so my slope should be positive. Again, how fast? That's where you could draw it a little differently than I do, but it should be moving up. And so there is a possible sketch of the original function f of x. You could sketch it slightly different, but it should have that basic parabola shape. Alright, my vertex, my critical value, should be at the 4, somewhere at the 4. Again, you could put it up, down, anywhere you want, so long as it's at the 4. And then how fat or skinny you make your parabola is up to you. Alright, so like I said, when I have the example filled out, on the filled out notes, I actually did different than this, just to show you that there's other possibilities. But it should have this basic shape. It should be a parabola opening up, where its vertex is at 4, and that's its critical moment. Second example. Again, we get a little more complex. We started out with a critical derivative that was just a straight line. Now I did a parabola-shaped derivative. So this is a derivative again. So I drew it in red. The derivative. Right, and so, again, this is a graph of the derivative. And this one's actually harder. This is a harder example. And so the last one is also a trickier example, because this is a special case. Alright, so first, the red function here is my derivative. And so, again, we start off with, so I'm going to write these in red. Is the derivative have any zeros? Find its zeros, which, remember, represent critical values. Well, it does have 1, 0 at x equals 0. So at x equals 0, I have a critical. Which, again, it does give me the horizontal tangent case. So that means 0, f of 0 should have a critical moment. And specifically horizontal tangent case, a stopping point. Alright, so I know my original graph should have a critical point at 0. Alright, now the tricky part is you'll notice it bounces at 0, right? Meaning, when I figure out when the derivative is positive, well, it's positive everywhere but at that moment, right? This entire side is positive, this entire side is positive. And so, from negative infinity to the 0, it's positive. Now at 0 it's not. It's not at 0. But then on the other side, it's positive again. And so it's positive everywhere but at the critical moment when it's 0, right? 0 is neither positive or negative. So it's positive up to the critical moment, stops, and then positive again after the critical moment. And so that means it's never negative. So that tells me the original function f of x, the original, is increasing from negative infinity to 0, stops at 0, because that's a critical moment, but then continues to increase again after x. This is one of my special cases. It means that is a critical point. It is neither a max nor a min. It is just a critical moment. Alright, so my critical point f of 0 is just a critical. It is not an extrema because I didn't switch directions. Alright, so the graph then. The possible f of x sketch. Alright, again, on the notes, I graphed it on here, but I'm going to actually graph it below based on my information. Alright, so x equals 0 is the important point. So there's my x equals 0 point. Alright, so the first thing I'm going to mark off is I'm going to draw my critical point. And again, this is where your answers might vary. You can draw that critical moment anywhere on the x equals 0, which is my y-axis. You can draw it anywhere on the y-axis. So in the example I gave, I drew it up here. This time I'm going to draw it down here. Alright, so I'm going to say there's my critical point. 0, f of 0. It's my critical. Alright, so that's my stopping point, which means that'll be a vertical tangent. It stops at that moment. And only at that moment. Everywhere else it's not. And so then to graph it correctly, it should be increasing on both sides, stopping at that moment, which means from negative infinity to this moment, it's got to come up and increase to it. So when I draw this, it's going to come up, flatten out, so it's going to have that S shape. Stopped, but then after that moment, it didn't decrease, so it's not moving down again. It continued to increase after that moment. And so there's the shape. So it's sort of that S shape. There's so the possibility is you could have drawn this S shape anywhere up and down. So I could have drawn it, again, I think I did in the notes, up here. Anywhere you want, as long as it has this S shape. There's a stopping moment at the 0, increased on the left of it, increased on the right of it. So as long as it has this S shape, and how curved you make that S shape, that's where it could differ, but it should have an S shape like this, and it should be somewhere on the x-axis where it has that kink in it. And there's my possible sketch of my function. The last, so that was a tough one, and then the last example. So kind of, we go up in more difficulty, right, with each one. The first one was a simple case. We got a little trickier in the second case, and then this one again is a little more complex. Although I actually think this one is easier than the last one because it's not a special case. But it does throw students off because it's a little more, again, complex. All right, so here's again, this is the derivative. So this is the red function is the derivative. First thing we find are the zeros, where it crosses the x-axis. It does have two zeros. It's got a 0 here at 0 and at 4. So at x equals 0 and at x equals 4, those are critical values. Again, specifically horizontal tangent cases, which means 0 f of 0, which again, I don't know what f of 0 is, but it is a critical point, and 4 f of 4. Those are critical points, where I've actually got a stopping point. All right, now I figure out where my derivative is positive and where my derivative is negative. And this one actually, like I said, it's easier than the last one because it switches both times. It's positive, so I'm going to highlight the positive in blue. So it's positive here, right, above the x-axis here, and then positive again over here. So my derivative is positive from negative infinity to the first critical value 0, and then again from the second critical value 4 to positive infinity. Which means that translates into the original function, the original, not the derivative. The original function is increasing from negative infinity to 0, and then again from 4 to positive infinity. Alright, so that's an important aspect of my graph. So it's got criticals at those moments. It increases on the tail. Between the two values, even though it's got weird stuff going on, but if you look between 0 and 4, this entire piece is negative. And so my derivative is negative. All my slopes are negative from 0 to 4 between the two critical moments, which means my original graph, I wanted to write derivative, is decreasing between the critical values 4 to 0. And so those are the important aspects that I want to graph when I sketch my graph of my original function. All right, which I'm actually going to, so I'm going to erase this and sketch it on, since this has got a nice grid. I'll sketch it on the grid here. Or you can sketch it below like I did with the last example. Alright, I'm going to draw it in blue, since the graph here is drawn in red. So first of all, mark off your critical points. Now this one I want to be a little more careful with my critical points because of the behavior of it. I know from 0 to 4 it's decreasing, right? So I'm going to kind of use this last piece of information, which means the critical value at 0 should be higher than, above, the critical value at 4. And so when I go mark off my critical values, I make sure that I put 0 above 4. Again, I can mark the 0 off anywhere I want on this graph. So I'm going to mark it up here at 3, 0. Again, that's just a random point I picked. There's my critical value at 3, 0. So that's the 0, f of 0 critical value. Then the other critical value 4, I can't mark it above because I've got to be decreasing down to it. So I've got to make sure I've got to go below. And you can go anywhere you want. Since this looks like it gets fairly negative, I'm going to go maybe here. Again, this is where it's arbitrary. You just have to make sure it's below the 0. So there's my second critical value at 4, 0. And then my graph should reflect where it's increasing and decreasing. So I'm actually going to start off with this decrease. Right? It's got a decrease between the 2 points. Now, if you kind of follow the shape of the graph, it decreases slowly initially, and then it decreases really fast until it approaches this moment. And so you can kind of, if you want to, you can kind of reflect that. So it's decreasing slowly, and then all of a sudden, somewhere around here, it starts to shoot down pretty fast. All right, and it's up to you how you, again, this is where it's a possible sketch. Actually, I approached it a little too fast. Should then slow down so it's still a curved shape, not a corner shape. All right, and so there's my decrease, right? Decrease between 0 and 4. Everywhere else it should be increasing. And so after the 4, it should be moving up, right? Increasing from 4 to infinity. And so that's an easy one. I just draw this one up. The hard one for students is this one. Increasing means I'm moving up to the point, so I start below it and move up to that point. And so there's the blue line is my, possible f of x. It's possible because so long as it has sort of this shape, but where and how steep the lines are, students can vary. All right, so this one actually does reflect to what I have in those because I think it's the easiest way to go. But this would be, so it needs to have this S shape where the 0 should be the maximum, right? This should come out of max. And the 4 should come out of minimum because of the way the shape is. Because I know this last piece of information, my 0 should be higher than my 4. That's sort of the key piece there. All right, and there's the sketch of my graph. So hopefully that makes sense. Again, this one is tricky for, when I was first learning calculus way back when, for some reason I also had, this was, particular aspect of this was the part that was difficult for me. So do make sure you look at it and hopefully understand it. When you're given the graph of the derivative, sketching the possible graphs of the original function, kind of take it piece by piece, write out all the information that they give you, and then make sure your sketch reflects that information. And sometimes you have to start over, all right, to double check and make sure that your graph matches the information. And that finished up 3.1. So 3.1 was a big section. I did a lot of examples, and again, I did more examples than you necessarily need. You don't have to watch them all, but maybe go through and watch the ones that you think are a little trickier. All right, and so there is the finished up of 3.1.